So this is the 2009 paper, question 6, and we're looking at snowboarding for lots of fun. A snowboarder of mass M rides over an icy ledge onto a horizontal surface below. The snowboard leaves the ledge at 0 meters per second in the vertical direction and at only a very small horizontal velocity. So what does that tell us before we get into the question? Leaving at 0 meters per second in the vertical direction means the initial vertical velocity is 0, so we might have to do a calculation at some point, or that's just going to be important in terms of maybe kinetic energy, because being used to find a final velocity at the bottom of the cliff, because initial vertical velocity, you'd just be adding the gravitational potential energy. Anyway, that's just preempting things. And very small horizontal velocity means it's essentially going to drop straight down. Okay, so question. A, assuming that the centre of mass drops by a distance of b through the bending of the knees, on impact, show that the average reaction force acting on the snowboarder is this, Fr equals mg in brackets 1 plus h over b. So the bending of the knees, the person's going to hit the ground and they'll be in an upright, this is a profile position, in an upright position, there's their knee, and they're going to bend, so that distance is going to drop down. Okay, now traditionally, if you've ever seen snowboarders, what they usually do is they sink their bums right down to the ground, particularly when they're changing direction. Skateboarders do a similar thing, surfers do a similar thing. I don't think it would be too different with this, but we're considering the knee movement here, so that does play into something a little bit later on, but we'll see. So anyway, how do we do this? I can, just looking at the formula here, I can see a few elements that could be useful. Mg is a bit of a clue towards gravitational potential energy, and we've got some heights and some vertical distances here, so there's going to be something to do with gravitational potential energy. That also gives me a clue that we need to deal with energy changes in the system. That's going to be our consideration. So at the start, the total gravitational potential energy is going to be mgh plus, now this is the important bit, there's also this extra, because we're assuming at the top that they are in a upright position with minimal bending of the knees, and then at the bottom they're actually going to crouch down. Let's see if I can, you get the idea, so that there's a change in height from here as well, which is equal to b. So we've got two heights. We've got actually two distance measurements. We've got the height, and then we've got the small change in height, which is which I'll just write as b. So we've got h and b, just to be consistent with our equation here. Yeah, I've lost my colour. There we go, and my train of thought. So we've got two gravitational potential energies to deal with. We've got the height from the drop, which is gravitational potential energy, and there's the gravitational potential energy lost from mgb, from the small bending of the knees distance. So that's your total energy, or total even energy at the top, yes. And then at the very bottom, all of that, well, not strictly speaking, that energy will be converted to kinetic energy. But remember, before the bending of the knees, you're also going to have that mgb, which is going to be awkward and tricky. We don't know quite what how to deal with that. But at the very, very bottom, we know that the difference in energy between that kinetic energy plus the mgb available is going to be equal to the work done by the person who has applied a force to resist this downward movement times by the distance. In this case, the distance is going to be b. So this is quite useful for us. The Fr, the reaction force acting on the snowboarder, which is equal to the work done by the snowboarder, is going to be the force, oops, I've got this a little bit mixed up. Sorry, work, that's what I'm trying, is Fr, just putting this work equation in terms of things that we know to deal with, Fr times b. So work equals Fr times b. So that same work, if we're looking at our energy changes, is equal to this, the energy at the top, equals the work done by the snowboarder to decelerate. And yeah, so all of that gravitational potential energy, the height of the fall plus the height of the knees bending, will be equal and opposite to the work done. So we can actually ignore this bit of energy in the middle, because that's an awkward one anyway, mixing kinetic energy and velocities and all sorts when we're dealing with the formula. So what do we get? We get FR times by B equals mgh plus mgb. And I think that actually has all of the elements of the things we're considering. So let's just proceed. FR equals mgh plus mgb, and we're dividing both of those by b. It's going to cancel the b on that side, but it's going to leave the b on this side. So we've got a sort of division there. And we're going to end up with mgh over b plus mg. And we can take the mg out, and then we've just got the h over b plus, mg divided by mg is 1, which is exactly the same as what you have in the box. That's what we're after. Okay, except rearrange instead of being h over b plus 1, it's 1 plus h over b. Anyway, by using a height of 3 meters and a reasonable estimate of b, calculate the size of the average reaction force experienced by the snowboarder. Comment on how the actual force might differ from the average force. Well, I want to deal with that last bit first. So the actual force, if you were to consider a graph of the force against time, it's going to start off slowly, it's going to peak, and then it's going to decrease as well. So there's that peak. The average will be much lower, so the average is somewhere around here, and that's what you're interested in. So that might be the average force, which is what we're calculating. And in our calculation, we have got mg, so the height is 3 meters. We're not told the mass, so I think we're meant to calculate this one in terms of mg. We could put in g as well, but let's just stick with that. So h is 3 meters, so 3 over b. Reasonable amount to bend. This is a tricky one, because when you consider how you stand and how your feet are connected into a snowboard and how you would bend, you might only be able to bend down, say, 10 or 20 centimeters at a knee joint without sort of toppling over. The answers actually suggest 50 centimeters, 0.5 of a meter. So I'm just going to use that for this situation here, but as long as you are consistent and reasonable in your estimates, I think it probably wouldn't matter too much. But anyway, plus 1, so what was that? 3 divided by 0.5 is 6, plus 1 is 7, so our reaction force is going to be 7 mg, and that's going to come into play later on, which does, your estimation does affect how your response will be later on, but yeah, we'll see how we go with that. C. Show that the time to come to the stop excuse me, is given by t equals b square root 2 over gh, and discuss the effect of landing on soft snow. A sample calculation is required. Okay, so there's two parts to this question. It's good to identify the two parts. So we've got and as the separator, the